Good evening. This is going to be a YouTube video for Lecture 1 of Computer Science 203, Discrete Structures at the University of Maryland, Baltimore County. Classes, of course, have been canceled Monday because of the snowstorm. So I'll get this out so we can keep to schedule. And we'll go over the first lecture, a lot of which is just introduction, and a little bit is on the content in the text. But at least we'll get this underway, and so we won't be falling behind schedule. My name is George Ray. I'm going to be the instructor. Of course, our office, our classroom's going to be in the Performing Arts and Humanity Building, room 234. I'll be holding office hours from 5 to 5:30 on Monday and Wednesdays in that room. And in addition, I'll hold office hours on Blackboard Collaborate from Sunday from 3 to 4. And I'll be sending out another YouTube video link for you to look at for how to get a Blackboard Collaborate set up and running on your PC. We do have a grading assistant, Aishwari Bida, and she'll be working with us to grade coursework this semester. Some of my background, I was actually sitting in your seats 45 years ago. I attended the University of Maryland. Back then, the price for a semester of tuition was $236 for the whole semester, and that included unlimited courses. Obviously there's a practical limit, but the $236 went a long ways back then. I have bachelor's degrees in computer science and accounting, a master's degrees in computer science and marketing, and a doctorate in management. I've been in the IT field for 40 years, working as a programmer and a database analyst. And in addition, I was in the United States Marine Corps for 4 years as a tank platoon leader, an anti-tank platoon leader, an intelligence officer, and I was in the Air Force Reserves when I left active duty as a computer and communications officer in the Air Force. The textbook we're using is one of the standards, Discrete Mathematics by Susanna Epp. It's a very popular textbook, although quite expensive. You'll find it in the bookstore, and I'll bring a version of it to class on Wednesday. We'll be using Blackboard to coordinate the course. On Blackboard, I'll have our syllabus, our schedule, lecture notes, any special readings that might be appropriate for a particular topic that we're going to be covering. This semester, we're going to cover variables, relations, functions, and sets, the logic of compound statements, the logic of quantified statements, direct proof and counterexample, sequences, mathematical induction, recursion, and graphs. These are all topics that will benefit you in your further studies in computer science and also in your career. And it's becoming even more important with the advent of quantum computing, which is proven to be at least as efficient as classical computing in most disciplines, and orders of magnitude more efficient in many disciplines. So this kind of grounding is going to be very important. So let me give a quick demo of Blackboard and how we'll be using it in the future. First, we go to my UMBC and log in. And then once we've done that, we'll click on the Blackboard button. So here we are at my UMBC. I've logged in. I'll click on Blackboard, and I'll select the particular course, Discrete Structures. And here I've got my menu on the left side, the left navigation menu. I can click on Syllabus, and I'll see the course syllabus that goes over topics germane to the course, and also the schedule, so you can have an idea of what's coming up. And in addition, we have our lectures. And you can, in class, bring this up, and you've got the lecture materials for that particular evening, and prior to that if you want to study in advance. We also have an assignment section, so that's where we'll have homework assignments, and of course I'll be saying in class what homework assignment is assigned and when it's due, but in addition it's on the schedule and it's on the homework itself. And it's loading, and you can see the date that it's handed out and the date that it's due. In addition to homeworks, we have exercises. Homeworks are graded, and they will count towards your course grade. Exercises are not graded. They're just particular exercises in the book that I thought were particularly germane to the topic, and would be good practice for you to go through and do them. So they're recommended exercises. In terms of course grade, in the syllabus you can refer back to this. But we're going to have 6 homeworks and 3 exams. There we go. And each one of the homeworks will be worth 5%. So with 6 of them, that's 30% of your grade. There'll be 2 midterm exams. Each one of those are worth 20%. So that's another 40% of your grade. And then there'll be a final that's worth 30%, and that gives a total for 100%, determined by the 3 exams and the 6 homeworks. And the other aspects of the course policy are in the syllabus as well. Blackboard Collaborate, and again I will be sending out another video on that topic, but in my menu, which is an instructor's menu, it's under Course Tools. You'll have a Tools menu as well. It might be located in a slightly different location, but you would click on Blackboard Collaborate, and then you would join the room. And of course download the launcher and join the Alphas Hours Sunday from 3 to 4. And again, I'll send out a video on Blackboard Collaborate on how to get that set up and running. All right, so Blackboard again is going to be how we coordinate this particular course. And we'll also use email, and you'll be submitting your homework using the GL submit function that's available. Some of you may have used it in Computer Science 201. I'll give a demo of that on Wednesday for those of you who haven't seen it before. And we're getting the class master file set up right now. So that's the brief introduction to the course. The first topic we'll be covering is variables. And this is kind of a review of the mathematics you've had in high school. So there's 2 uses for a variable. To consider the first use, think of a question like this. Is there a number with the following property? Doubling it and adding 3 gives the same result as squaring it. In this sentence, you can introduce a variable to replace the potentially ambiguous word "it." So you would rephrase this question as, is there a number x with the property that 2x plus 3 equals x squared? The advantage of using a variable is that it allows you to give a temporary name to what you're seeking, so you can perform some concrete computations with it to help discover its possible values. So to consider a second use of variables, consider the statement, no matter what number might be chosen, if it is greater than 2, then its square is greater than 4. So in this case, introducing a variable to give a temporary name to some arbitrary number you might choose enables you to maintain the generality of the statement, and also allows you to replace all instances of the word "it" by the name of the variable, and that way you avoid ambiguity. So we would rephrase the question or the statement as, no matter what number n might be chosen, if n is greater than 2, then n squared is greater than 4. Okay, so let's go ahead and just do an example of how we might rephrase things with variables. So we'll ask a question, are there numbers with the property that the sum of their squares equals the square of their sum? So let's just assume there's two numbers that we're dealing with. So we can say, are there numbers a and b with the property that a squared plus b squared equals a plus b squared? Or another way we might phrase that is, are there numbers a and b such that a squared plus b squared equals the sum a plus b squared? Or do there exist any numbers a plus b such that a squared plus b squared equals the sum of a plus b squared? As another example, let's look at, given any real number r squared is non-negative. So we would, we ask the question, given any real number, its square is non-negative. So we would rephrase that as, given any real number r squared is non-negative, or for any real number r squared is greater than or equal to 0, or for all real numbers r squared is greater than 0. Okay, one of the things we'll be doing shortly is looking at mathematical statements and looking to determine the truth of those statements using a formal system of logic. So we'll go ahead and have an introduction into mathematical statements our first evening here. So there's three types of statements that are important in mathematics, and they are universal statements, conditional statements, and existential statements. And a universal statement says that a certain property is true for all elements in the set. And an example is, all positive numbers are greater than 0. So that's a property of all positive numbers. They're greater than 0. A conditional statement says that if one thing is true, then some other thing also has to be true. And an example there is, if 378 is divisible by 18, then 378 is divisible by 6. And then, given a property that may or may not be true, an existential statement says that there is at least one thing for which the property is true. For example, there is a prime number that is even. So not all prime numbers are even, but there is at least one that is even. So universal statements contain some variation of the words for all, and conditional statements contain versions of the words if then. A universal conditional statement is a statement that is both universal and conditional. So here we combine two types of statements, universal and a conditional. So one example of that might be, for all animals, A, given it a variable name. If A is a dog, then A is a mammal. So we've got a universal statement for all animals, and then we've got a condition. If A is a dog, then A is a mammal. So that's a universal conditional statement. And one of the most important facts about universal conditional statements is that they can be rewritten in ways that make them to appear to be purely universal or purely conditional. So again, let's take some more examples. Let's look at the statement for all real numbers x. If x is non-zero, then x squared is positive. So we can make this into purely a conditional statement by saying if a real number is non-zero, then its square is positive for A. For B, we can make it into a universal statement by saying for all non-zero real numbers x, x squared is positive. Here's another way we can make it conditional. In C, if x is a non-zero real number, then x squared is positive. And yet another way we can make it a universal statement. Again, universal statements are going to have all or every or any as qualifiers. So we say the square of any non-zero real number is positive. And another universal variant would be all non-zero real numbers have positive squares, or squares that are positive, square values that are positive. Okay, another combination that we can have from our three fundamental types, universal, conditional, and existential, is a universal existential statement. So a universal existential statement is a statement that is universal because its first part says that a certain property is true for all objects of a given type. And it's existential because its second part asserts the existence of something. For example, we have every real number has an additive inverse. So this property has an additive inverse applies universally to all real numbers. So has an additive inverse asserts the existence of something, an additive inverse for each real number. However, the nature of the additive inverse depends on the real number. Different numbers have different additive inverses. So not every number is an additive inverse of a number, but all numbers have an additive inverse. So the additive inverse is an existential aspect of that statement, and all real numbers is the universal part. So let's take an example here and look at a statement, every pot has a lid. So we can rephrase that, and instead of saying every, we can use another qualifier, all, and we can say all pots have lids. So that's really just a restatement of that universal. But we can also say, let's look at it more like a universal existential statement. For all pots P, there is a lid for P. So not all lids fit on every pot, but there is at least one lid that does fit on a pot, and all pots have a lid that fit. Another way we might want to look at this, and again, this is expressing it as a universal existential statement. For all pots P, there is a lid L such that L is a lid for P. Another possible combination from our three fundamental statements are existential universal statements, which are just the reverse of what we just looked at, universal existential. So an existential universal statement is a statement that is existential because its first part asserts that a certain object exists, and it's universal because its second part says that the object satisfies a certain property for all things of a certain kind. So, for example, let's look at the sentence. There is a positive integer that is less than or equal to every positive integer. So we see the earmarks of existential. There is a, or there exists a positive integer that is less than or equal to, and here we see the characteristic of the characteristic qualifier of a universal, every positive integer, or any positive integer, or all positive integers. So this statement is true because the number 1 is a positive integer, and it satisfies the property of being less than or equal to every positive integer. So again, let's look at some examples. Looking at the statement, there is a person in my class who is at least as old as every person in my class. So we can say, rephrasing it, some person in my class, and again, some like exists or there is an indicator of an existential qualification. So some person in my class is at least as old as every person in my class. Every, again, is the indicator of a universal condition. Another way we could rephrase that, looking at B, is there is a person P in my class such that P is at least as old as every person in my class. So there is A is the same as some, or it's also the same as there exists. In other words, there's at least one or more. And finally, we can rephrase it and say there is a person P in my class with the property that for every person Q in my class, P is at least as old as Q. Again, we've got every as our indicator for a universal. And we'll conclude tonight's lecture by just looking at the concept of limits. Some of the most important mathematical concepts, like the definition of a limit of a sequence, really can only be defined using phrases that are universal, existential, and conditional. They require the use of all three qualifiers. for all, for every, for any. There is, there exists, some, and the if-then. So here, for example, if we look at the limit as it was used in calculus, we can say that, okay, for a sequence of real numbers, the limit of an as n approaches infinity is L, means that for all positive real numbers epsilon, there is an integer n such that for all integers n, if little n is greater than n, then a sub n minus the limit that we're looking at is between a boundary of minus epsilon and epsilon. So there we've got all three of the qualifications. If, then, for each, there is, and for all. All right. Thank you very much, and I look forward to meeting you all on Wednesday.